Now, I talked about in my previous recording the concept of a difference of two squares when we were performing FOIL. To identify a difference of two squares, what you do need are two values that are perfect squares, separated by subtraction, hence the word difference of two squares. You've got two square numbers separated by subtraction. And to do those, you simply take the square root of the two values and then write them as two factors, the same roots of those factors separated by one by addition and one by subtraction. So you see the two examples. I've got 49x squared minus 144. The square root of 49 is 7, and the square root of x squared is x. So I've got 7x squared, and the square root of 144 is 12. So then I can write it as 7x plus 12 and 7x minus 12. You'll see in the next example that I still do have technically two squares, even though I have a to the power 4. Well, the square root of a to the power 4 is the same as saying a squared squared. And the square root of 81 is 9. So then I could say that it's a squared plus 9 and a squared minus 9. But look again, a squared is still a square number and 9 is still a square number. I can't do anything with a squared plus 9, but a squared minus 9, once again, I could state that that's the same as saying a all squared and 9 minus 3 all squared. Obviously, like I said, the a squared plus 9 remains. And then I state the difference of the two squares. So let's look at a few examples. The first example, x squared minus 64. We know that we can state this as x all squared minus, and the square root of 64 is 8 all squared. So the difference of the two squares is x plus 8 times x minus 8. Let's look at our next example. I've got 4a squared. That can be expressed as 2a all squared. And the square root of 49 is 7 all squared, giving me a difference of 2 squared of 2a plus 7 and 2a minus 7. And our last one sometimes can be tricky for some people. I've got 1, the square root of 1 is itself. And the square root of 121 is 11. And the square root of y squared is y. So then I could state that it's 1 minus 11y and 1 plus 11y. Again, it doesn't matter what order you write them because a times b is the same as saying b times a. So let's just look at two more examples. For these last two examples, you have two examples where you need to first find your greatest common factor and then factorize. So if you look at our first one, the greatest common factor in this one is a 2. The 2, when divided out, leaves me with 9x squared and 1. The result is a difference of 2 squares. So it's 2 times 3x all squared minus 1 all squared, difference of 2 squares, giving me a final result of 2 times 3x plus 1 times 3x minus 1, difference of 2 squares. Now we look at our final example. Once again, I need to identify what is the common factor. The greatest common factor in terms of the constants is a 2. Each term contains an a and nothing else in common between the three. What that leaves me with is 36x squared plus 12xy plus y squared. Now this can be factored once again if we consider the factors of our leading coefficient. Now there's a lot of them. There's 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. All well and good. Since everything's positive, that makes this a little bit easier, or a lot easier. So we think of, since my final coefficient y squared is just 1, we know the square root of that, or when I have two terms multiplied by themselves to equal y squared, it's y times y. So we don't have to worry about that. So we just need to think of what two terms multiplied themselves also add up to 12, but multiplied to 36. In this instance, it is 6 and 6. So I still have the 2a. And technically what I have, if you think of it in this way, I have 6x all squared plus 6xy plus 6xy plus y all squared. So that gives me 2a times 6x plus y times 6x plus y. What this is known as is a perfect square. So that can be simplified even further as 6x plus y all squared, because that is a perfect square as opposed to a difference of two squares.